Today we'll derive the velocity vectors for the motion of a particle in circular motion, and we'll do so in polar coordinate system. In polar coordinate system, the position vector is this vector r defined from the origin of your coordinate system to the position of the particle. The unit vector would be this r hat vector, which is radially outward, and this theta hat vector, which is tangential and perpendicular to the r hat direction. We'll assume here that the motion of the particle is confined to this circle of radius r. The implication being that then this position vector would have a constant magnitude, which is the radius of this circle, and we'll call this r without the vector notation. So in polar coordinate system, our position vector can simply be written as this magnitude r in the r hat direction. To get the velocity then, we take the time derivative of this position vector. The magnitude r being a constant with time will come out of the derivative, but we'll take the time derivative then of this r hat vector. In polar coordinate system, this time derivative of r hat is not trivial because the direction of r hat changes with time. So at a later time, for instance, when the particle is over here, the r hat direction will be radially outward this way, and the theta hat direction will be here. So both r hat and theta hat will constantly change direction as a function of time. So to calculate an expression for this dr hat dt, we had previously derived a relationship between the r hat and theta hat unit vectors with I hat and j hat, our unit vectors in Cartesian coordinate system, which do not change with time. We've established that r hat is a rotation from the I hat direction, okay, meaning that this r hat direction is a rotation of an angle theta from the x-axis. So similarly then, the theta hat direction, which is perpendicular to the r hat direction, will be a rotation of an angle theta with respect to the j hat direction. We've then derived that r hat is going to have a component of cosine theta in the I hat direction, that's this component, plus sine of theta in the j hat direction, which is this component. And theta hat is going to have a component in the minus I hat direction, which is then minus sine of theta, plus a component in the j hat direction, which is this adjacent, which is cosine theta in the j hat direction. So from this expression, we can take the time derivative dr hat dt, the derivative of cosine giving us minus sine of theta, and because theta can change as a function of time, then we have to do a chain rule to get d theta dt. That is the derivative of this expression in the I hat direction. And the derivative of sine theta is going to be cosine of theta, and by the chain rule, d theta dt in the j hat direction. So by taking the time derivative of this r hat vector, in fact, we pick up a d theta dt, and the remaining expression minus sine of theta in the I hat direction plus cosine of theta in the j hat direction is exactly what theta hat is. So this expression in parentheses is exactly what theta hat is. So the time derivative of dr hat dt gives us d theta dt in the theta hat direction. Now that we've derived an expression for the time derivative of dr hat dt, we are ready to continue our derivation for the velocity. Then the time derivative of the position vector, which gives us the velocity, is r, which is a constant, times the time derivative of r hat, and the time derivative of r hat gives us a d theta dt in the theta hat direction.